Let's look at example number 9. This one is about soil strength. Pause the video for a couple of minutes and we'll be back very shortly. Okay, we're back. This one is about direct shear test. We have the dimensions of the container, diameter of 71 millimeter, and we have the height 25 millimeter. We know the normal force, and we also know the shear force, asking for the friction angle of the soil. So first of all, I kind of want to refresh your memory about direct shear test. We're talking about a container, kind of for cross section, kind of looks like this. That you put your soil sample inside. You leave a little gap in between those two half boxes, and then you can fix the bottom half, and you apply a horizontal force, F shear, and you can also apply a vertical force to apply the appropriate level of normal stress, and the soil is gonna fill along this surface, so that this equipment can tell you the cohesion and the friction angle of the soil, of the tested soil. So if you don't remember the equation of for direct shear test, you can open up the reference manual, and it is right over here. This is the failure mode. This is the failure criteria. The Moore-Coulomb failure criteria over here. That your TF, that's not T, sorry, that's tall F is cohesion plus sigma n times tangent friction angle. So let's just write that equation and let's try to solve that. So as we just looked at, that your TF, I'm sorry, again, tall F, your shear stress is the cohesion plus sigma n times tangent friction angle. Let me explain this term one by one. So this is the shear stress at failure, shear stress. This is the cohesion of the soil. And this is the normal stress. And of course, the friction angle is the friction angle we want to solve for this problem. So technically, you should have a friction angle prime, but I think the reference manual did a pretty terrible job of just did not really distinguish the effective stress values with the total stress values, but stress values. But I think that's fine. So for this one, cohesion is easy because whenever you see dry sand, you can pretty much consider the cohesion is 0. So that's just dry sand. Their kind of lack of the fine contents is dry, does not have water inside, so the particles wouldn't be kind of you just basically have no cohesions. So now the equation is a little bit easier. That we're basically talking about tangent friction angle is your tall F over the sigma n, right? The tall F over sigma n. So after we figure out the tall F and the sigma n, we should be good to go. Well, we do know the normal force. We do know the shear force, but we don't know the stress. But as you can recall, the relationship between force and the stress is essentially the force over an area, right? And for this one specifically, we're talking about the cross-section area right over here, the entire surface that the failure has happened on. And that cross-section applies both for the vertical stress, for the vertical force, and also apply for the shear force. So your tau F is essentially your 276, that's the shear force over the cross-section area of this specimen. And your normal stress is basically your normal force, 594, over the same cross-section area. So you see, you both have cross-section area here. You can actually cross off the cross-section area. You don't really have to calculate that cross-section. But you can also choose to calculate the cross-section using the diameter of 71 millimeter, but you don't really have to in this case. So, but basically 274 over 594, 276 over 594, that is the tangent friction angle. This value is 0.465, and then the friction angle is arctangent 0.465. We're talking about 24.9 degrees. So the answer B is the right one. Okay, so, well, that's pretty much about it for example number 9.